Sir, we are very much thankful that you have joined us, sir. And you have spent a lot of time. Sir, shall we start, sir? I hope almost 20 attendees are there. With your permission,
yes,
we will.
Please.
Yeah.
Yes, please. Yeah.
Shall we? Well, good evening, everybody. Myself, Dr. Venkatramana, the convener for this program. I would like to welcome all the participants and the speaker to this session number 2. So the yesterday's session was very good. We were thankful for the resource person, and I request all the attendees to concentrate on this session also and try to learn whatever the points have been put forward. So this is a platform where we people can have some exposure in terms of various aspects. As such, we alone cannot have. So the platform is the best platform where the most of the learned persons will try to put their points and views, which may be very much helpful to the aspirants, researchers, scholars, etc. Once again, I welcome you all and have a nice evening for the next couple of hours. Thank you. Professor Jay Prakash. Please, Professor Jay Prakash. Yeah, please. Okay.
Thank you, sir, for your valuable introduction. Thank you for welcoming our today's speaker, Dr. Y. Ravi Kumar, sir. Good evening, one and all. Myself, Jay Prakash B., Assistant Professor in the Department of Mechanical Engineering, Ballari Institute of Technology and Management, Ballari. Now I'd like to introduce our today's resource person, Dr. Y. Ravi Kumar, Associate Professor in the Department of Mechanical Engineering, National Institute of Technology, Warangal. He is in the teaching profession since 20 years. He has received his bachelor's degree in mechanical engineering from JNTU Kakinada in the year 1999. Then he pursued Master of Technology in Computer Integrated Manufacturing in 1999. Then he, Master Technology in SIM, that is from PSG College of Technology, Coimbatore in 2002. And PhD in Mechanical Engineering from Osmania University, Hyderabad in 2011. He taught various subjects at UG and PG level. Being a supervisor, he has guided 5 PhD scholars, 45 MTech, 16 BTech projects. Sir has participated more than 250 seminars, conferences, workshops of regional, national and international conferences, 6 national conferences, 21 international journals, 41 international peer-reviewed conferences, 5 national journals and 1 textbook engineering graphics and 2 book of chapters. His research interests include rapid prototyping and tooling, CAD/CAM and biomedical applications of additive manufacturing. Our beloved resource person, awarded and honored by Young Engineer of the Year 2009, award by the Government of Andhra Pradesh and Institute of Engineers, India. Received Outstanding Best Technical Paper Presentation Award in 2007 from IISc Bangalore and Best Technical Paper Award, Second International Conference on Recent Trends in Metallurgy, Material Science and Manufacturing from NIT Tiruchirappalli, and received an international travel grant to tune of Rs 1,09,097 rupees from the Department of Science and Technology, DST, New Delhi. Also, he is served as a BOS member, Vagdevi College of Engineering, Warangal, Aditya College, Surapalam, then Narsarapeta Engineering College, Narsarapeta, then Chaitanya Bharati Institute of Technology, Hyderabad. It's our pleasure, sir, to have you with us today, sir. Thank you very much, sir. Now I request today's speaker to take over the session. Sir, over to you, sir. Thank you very much, sir.
Thank you. Good evening, one and all. First of all, I would like to thank the organizers of this event for organizing this nice event. So, is my screen is visible, sir?
Yes, sir, it is visible.
Yes, sir, it is visible, sir.
Okay, thank you. Yeah, first of all, let me thank the organizers putting the effort to conduct this kind of a program. So it's a hybrid program, which the first week will be online and the offline followed by. So I'm not 1 minute actually. I'm not getting my. Is my slides or yeah fine. Is my
It's
slides are
moving.
moving?
Yes,
Yeah.
sir, it's moving.
Okay.
Good. No problem.
Thank you. Thank you.
Go on, sir.
Yeah, thank you. So yeah. So thank you for the opportunity given. I hope this is the second day of the program. And we know by this time 3D printing or otherwise called as additive manufacturing. So it's going to play a major role in industry 4, right? So, and we'll see that how this technology we can say substantiate this statement whether it is true or not. So this is going to be the outline of my presentation for the next 2 hours of talk. So if you see broadly, my talk will be organized in 2 parts. So first part will be introduction, a quick introduction to 3D printing and what is 3D printing and the steps involved in 3D printing, and of course 3D printing processes and some state-of-art applications. And then followed by the second part could be on the design aspects. So if you see the design for additive manufacturing, or otherwise called as the design for AM, DFAM, that is stands for. So my talk, second part of my talk, so it will be focusing on DFAM, that is design for additive manufacturing, otherwise design for 3D printing. So this is the second part of my presentation, and this is a general introduction to this. So, and why I should talk about these processes while designing your AM. So design for AM. So which you must have the you must know the intricacies of each and every process. So then only you are able to design your part as for the additive manufacturing constraints or as for the 3D printing constraints. So that's the intention. I made it as 2 parts. The first part could be so the general introduction and about the processes, and then how you can select a particular process. So based on your design for additive manufacturing. So probably, so my talk will be revolving towards design for additive manufacturing. So what is the design? What do you mean by design for additive manufacturing? So you may get doubt immediately that, so whether the conventional designs are not meant for additively manufacturing, right? So then we will discuss that also, like why you need a DFAM or a design for additive manufacturing is so important in the recent times. So whenever you talk about 3D printing or additive manufacturing, right? So let us start the first portion, that is introduction and the general applications, and followed by the design approaches. So you have some unique capabilities of additive manufacturing. So throughout my presentation, the word additive manufacturing and 3D printing both are synonyms. So that's my talk. So you assume that both are synonyms. So you have a unique capabilities of additive manufacturing. So that is part consolidation, and you have the capabilities of CCC, that is conformal cooling channels, to name a few actually. And you have the capability of printing a topology optimized structures, and you have a capability of fabricating bionic designs through additive manufacturing. And finally, I'm going to talk about, whenever you talk about DFAM, so which we need to understand the guidelines or the constraints of each and every process. So ASTM has classified broadly this into 7 categories. By this time, the previous speakers might have also emphasized on that. But anyway, so you have to select the right process for your right product, right? So then we need to understand the design constraints or the guidelines that we need to follow if you are printing a polymer, or if you are printing a metal or a composite, or even it could be ceramic. But this subject is a big subject. Normally we teach at NIT Warangal this course called Design for Additive Manufacturing for MTech Additive Manufacturing course. That is the course first time in India we started at NIT Warangal. So we teach this topic, or rather than this is a one course for them, 1 semester long course. So I will try to give the glimpse of that, but everything is not possible to teach within 2 hours. In fact, it's a 40-hour course, 1 full semester course. But anyway, I will try to give the glimpse of this design for additive manufacturing. So we need to follow certain guidelines or the rules in order to exploit your additive manufacturing capabilities. So in that process, you may redesign the product also. So that we'll see. And finally, you have a lot of challenges. Then what are the fabrication challenges in this 3D printing or additive manufacturing? So this is what I have planned for the next 2 hours approximately. So this is the plan, and followed by the discussion or the interaction. So I request you to note it down if you are having some clarifications or some doubts you are getting during my presentation. You can note it down and you ask me after 2 hours, right? So maybe between 9 to 9:30 we will spend for the interaction. Yeah, and then the industrial revolution. The first industrial revolution was during 1780s to 1860s, where you have a steam power or a water energy was the in a single word, it was the mechanization, right? So that was the first industrial revolution, where you have a mechanical production system instead of a cottage kind of industry previously, which you have. But from the first industrial revolution onwards, you have a mechanization came into picture, and second industrial revolution, where your assembly line concept has came into picture, and your steam and water power has been replaced with the electrical power, that is between 1870s to 1960. And coming to third industrial revolution, you have information technology, and you have computing and automation and electronics. So that was the during 1970s to 2010. And now we are talking about Industry 4, right? So when you talk about Industry 4, so what are the elements or the cutting edge technologies that Industry 4? So you have an autonomous system, which it will take some independent decisions, like it may be an automobile, or it may be a robot, or even it could be any system that will have an autonomous systems. And your computing now has been changed into a cloud-based computing, so which you can see in the recent times, right? And of course, which we need to get the integration. Yes, you have a CAD-CAM integration that is in third industrial revolution also, right? Where you have a CAD-CAM sim concept that came into picture. And even further, which we need to integrate these systems and simulation and IoT. So where you have your machine can be controlled, or even you can send the instructions, or you can receive the feedback from the machine through an IoT devices, right? So, and you have an AR and VR, that is augmented reality, virtual reality, and you have a big data analysis concept. And the biggest threat is security of your data. So you have a cyber security is coming up. And then what about the nature of manufacturing, how it is going, right? So undoubtedly, it is going towards additive manufacturing. So then you can see several, say, literature or the surveys are saying that by 2030, so your additive manufactured components, so it's going to be a trillions worth of parts or end products. So you know how much maturity this technology has to take if you talk about the end products. Though this technology started with a prototyping application, very well-known word called rapid prototyping. But now this technology, rapid prototyping technology, got matured into additive manufacturing. So it was a tool for the manufacturer, in fact, not a designer. Previously it was, right? And we can see several surveys, literature saying that it's going to be the promising technology, right? So under Industry 4. So then if you see a broad classification of manufacturing processes, so then first thing we talk about is a subtractive manufacturing process, right? So where the machining is an example of this subtractive nature of manufacturing. So the concerns could be a lot of wastage, right? You have a lot of wastage. We need to start with a bulk of material and keep on removing the material unless you get the required shape and size and dimension tolerance and so on. So during that process, sometimes you may waste 90% or 95% of the material, right? And another concern could be we need to invest a huge on the tooling investment, right? And sometimes the jigs fixtures should be designed and fabricated along with. And what about the complexity of the component? If the complexity of the component is so simple, like a flat surface, you doesn't bother much. But now your component, instead of a stepped kind of geometry, now you have a free form geometry, something like a simple coffee cup. So then what are the concerns that if you are working, though you are working with the CNC machining, a CNC machining center or a CNC turning center, if you are using it, but still we need to address the concerns. Why? Because you have a cavity here which is too deep to machine. So what kind of a tool or tool radius compensations and other stuff which we need to, and we need to design a fixture which it should hold from the bottom, right? So then we need to take care of designing, fabricating the fixture, and you have very sharp internal feature here, so which it cannot be machined without a tool radius compensation and so on. And you have an undercut here, right? So you have an undercut here, so where it requires a minimum 3-axis machine. So that those are the constraints. So if you talk about a subtractive manufacturing process, but if you have another hand, like if you have a additive manufacturing, say a process here, right? So where you could even able to make the part rather than without removing the material, you are adding the material from bottom to top approach. So I have a first layer here and I have a second layer and so on, right? So where I can reduce my complexity, 3-dimensional complexity into a 2D or a 2.5D complexity. So, and then there is no wastage of material. So hardly you doesn't have any wastage here, and there is no tool at all here. So your tool investment in case of CNC, it will go sometimes 30% or 40% of your total capital or investment, right? So, but you don't have a tool at all here, and we are not worrying about the jigs fixtures. It is a toolless manufacturing. It is a fixtureless manufacturing, right? So, and then we will talk about, then what about the complexity? So the complexity is a free of cost in additive manufacturing. So then we'll see how it could be done. And then of course you do have another classification called as a formative. Example is like, say you have forging or you have a molding, injection molding. So where we need to make a die.
Sir,
Yes.
sorry to interrupt, sir. Your presentation is not visible, sir. Will you share the screen once again, sir?
Is it? 1 minute. So right from the beginning, it is like that.
Yeah, it was visible, sir. Right now, it's separate. You reshare once again, sir. That's it.
1 minute. So I am stopping the presentation, sharing it, and again resharing it.
Yeah, sir.
So, but
sharing and then once again share, sir.
But I could not get my sharing option. So it is showing
Sir,
only meeting organizer.
Okay, sir.
Meeting organizers and presenters can share, but you are not allowed to share. That's what I'm getting a message at the share button.
In that case, you can just mail us, sir. I will share from my screen if it is required. Sir, we can just stop sharing and once again share, sir.
That's what actually, at the moment I stop shared, now
Yes,
I'm not, it was disabled. My sharing option in my Microsoft Teams, now it has been disabled.
Made you presenter, sir. So that you can share once again, sir. Just I will make you presenter.
Okay.
Just a minute, sir. Just give me a minute, sir.
Yeah, please.
Yes. I have made you presenter, sir. Now you can share, sir. That's all.
Yeah, now I'm getting this up.
Yes. Just a minute, sir. Participants, please see that your camera is off and mic is muted. And frequently do not leave and enter so that we keep on changing your status from presenter to attendee. Thank you.
My screen is visible now?
Yes, sir. Visible, sir.
Yeah, where we stopped somewhere here, right?
Yes.
Let me see. So whether I completed this,
This,
I don't know, you have to tell
this part
some.
completed, sir. Yes, sir.
Right. Yeah, then you talk about additive manufacturing. So where you can, you doesn't require any tool here. It is a toolless manufacturing if you talk about additive. And even your wastage is literally zero or maybe very nominal, right? And you doesn't require any jig or a fixer. It's a toolless or a jigless manufacturing. And of course, you do have the third category is a formative process, something like your forging or molding. So where we need to make a die again, that is the shape of the part that you are anticipating to fabricate, right? So then we need to design, fabricate a die or a mold, but the same story will repeat, right? So where in case of additive manufacturing, so it is even a die-less manufacturing where it doesn't require any die at all, but you are adding the material layer by layer from bottom to top. So you are reducing the three-dimensional complexity into 2D or a 2.5D, literally the uniform layer thickness. You are say reducing your complexity, right? So anyway, we'll see further. Now immediately in your mind, what could be the cost of this, say, cost per part if you plot the graph between cost per part versus the number of parts. And of course, initially, the conventional manufacturing processes, like it may be forming or subtractive, where you have much expensive if the number is small. But we do agree that you have exponential reduction in the cost, both as well as in formative as well as subtractive. But you can find a different trend, a linear trend in case of additive manufacturing. So your cost remains same, it's irrespective of number of parts. So that is what it may not be meant for mass production. But now the world is towards mass customization, but not mass production like the previous industrial revolutions. But whereas now it's going to be a mass customization kind of a slogan as coming to picture in Industry 4, right? And okay, then fine. And of course, you have some break-even point where you can select your technology, or like say, once you introduce the complexity of the part into this system, right? Say, if you the initial design of this component is like cylindrical, and you can see some welding might have done, and then you might have done some machining and so on, and it has been, say, assembled together, right? But it is very simple geometry as far as geometry is concerned. But designer has changed that design into a free-form design. Why has it changed is in order to improve the functionality of the system. So probably you might have redesigned this by taking the inspiration from the nature. So making a more weight conscious, maybe lightweighted structure, at the same time improving the functionality of the component. So then you talk about now the conventional manufacturing processes. Like say, if you want to machine this component, so then you know how much difficulty it is. We can expect the, if you try to plot the curve between the cost per part versus complexity, so we can get the reverse trend of this exponential increase in the cost once the complexity has been increased, right? So anyway, that's where additive manufacturing is shining now. Like say, whether you are producing this standard geometry like circular or cylindrical or all standard analytical geometry, but instead of that, you have the complexity is 4x times or 5x times, but you can produce at the same cost without increasing the cost, even though you have 4x times the complexity has been increased. So that is the beauty, right? Anyway, so in continuation with that discussion, like say, if you try to plot the graph between cost versus complexity, right? And where your conventional manufacturing processes, at the moment you increase the complexity of the system, so where you can see the exponential reduction, increase in the cost. But you can get the advantage here. So get the irrespective of increasing the complexity, but your cost remains same. So that's the beauty where you can achieve it with this additive manufacturing technology. So not only reducing the cost, if you compare with the exponential increase in the cost in the conventional manufacturing systems, so you can save a lot of money, right? And not only that, so means which we can say it is a complexity is a free of cost. It is not adding any additional cost, even though your complexity is now 5x times or 6x times. But everything you're getting a free, the complexity is free. And not only the complexity is free, so you are able to increase the functionality of the system. Like say you have, I think you maybe come across the conformal cooling channels in case of injection molding dies. So where in a conventional cooling channels, it means like if you are using a machining to drill, so you may be using a straight cooling channel, but without taking the concern of the shape, or you are not confining the shape of the part. But whereas, so you can have a conformal cooling channel, which is done through additively fabricated. So your cycle time has been reduced drastically because of your conformal cooling channel. So where your cost, if you compare with the conventional manufacturing, so it may take months together to design a die and fabricate it. But it's a matter of days, or your time scale is weeks, but not the months or the years in case of a conventional tool making, tool designing, right? And with the additional advantage of improving the functionality, the cycle time has been reduced, right? And you have the temperature dissipation. You have a uniform heat extraction from the system, right? Where you incidentally you have increased the functionality, the functional performance of the system. So that is through additive manufacturing. So you have a double benefit here. You have reduced the cost as well as you have increased the functionality of the system, right? And then what is a 3D printing, right? And this discussion will continue in the design aspects also. So for the general understanding, what is 3D printing? And so 3D printing is not a new, right? So you have the term called rapid prototyping, right? Rapid prototyping. So it is the former name of this technology, rapid prototyping, where it was evolved during 80s, the early 80s or late 70s or early 80s. So where rapid prototyping has came into picture. And now you may be calling that technology as additive manufacturing because of the maturity in the technology, and in a common common man name, maybe 3D printing. It is a extension of 2D printing, right? But if you are a mechanical guy or an engineer, so you know the capability of manufacturing. So then you may be calling that, you call that as additive manufacturing technology. But non-manufacturing, non-mechanical people, so they are very well versed about the 2D printing. Now that's what it is well known, recognized in the media or the common man, it's a 3D printing, right? But all are same. But what is the essence of this 3D printing or additive manufacturing or rapid prototyping? So we need to start with the CAD design or a digital design, right? So where do you get the digital design? So one way of doing it, go to your CAD/CAM system, and right from the scratch you model it, or you have another avenue where you can see my annotations. Actually, I am using some annotation tool. Hello, can anybody respond? Hello.
Hello, sir.
Yeah, are you able to see my annotations, which I am using my pen in the
Yeah,
PPT?
yes, sir. Very much
Yes, sir.
seen, sir. Can see.
Fine. Just I want to confirm. Simply I am using
Yes.
it, or you are able to see.
No.
Maybe
We
some-
can see it, sir. We can
Yeah,
very
maybe
much
some
see it.
lag. Maybe some lag it is coming, or it is
No.
lag without
It's
lag.
with your, what immediately we are seeing that.
Okay, fine. Thank you for your response. So we can even reverse engineer it or 3D digitize it, right? Where you have a physical component and use a 3D scanners or the digitizers to get the soft copy or a digital data, right? If it is already, your product is existing already, then you can digitize it and get the CAD model. Or you can, one way of doing it is use a CAD system, or another way is you have already a physical component, you reverse engineer it or you digitize it. And you have a third option, maybe in medical applications, you have a CT or MRI scan data, right? So where you can take, that is also digital diagnostic data, then where your journey will start. I hope the other speakers may be talking about the medical application. So, but like where you can interface this data to your additive manufacturing or 3D printing technology, your digital data should be ready. So whether it is done right from the scratch or digitized or getting from the medical imaging data, and from that you're going to get a physical component. Maybe you call that as a part or a prototype or a model or a end product, right? How do you see that product? Means what is your application? Like whether you are using a directly that you're using it in your system as an end product, or it is a component, or it is a model, or it is a prototype, right? So where that matters, like how you are using this. And of course, it depends on the characteristics or the quality of the part and what kind of material. We'll talk that also. And for your design for AM, it is very much needed. Like say, normally you decide first material and go for the functionality list next, or the second priority. But in additive, you have to give a priority to the function first and material second. Why it is, we'll discuss that. But the idea here is, okay, so you start with your journey by, without a digital data, nothing will be done, as we know that this technology is all about. So if you see the various steps involved, so first step, we should get a CAD model, maybe direct CAD, or maybe digitized data, maybe medical data, maybe gaming data, or somehow you get a digital form. Say I need to get a cup of coffee. That is my application. So then quickly I can go to any CAD system. I can quickly make the solid model or a wireframe model or a surface model. But solid is ideal representation, as we know that. And then that CAD data should be converted into STL file. So that is the de facto standard, like your FEM mesh. So here every time is a triangle. Why it is triangle? So it is the simplest form of a polyhedra. So it is a representation is not the goal, and we need to process further. We need to slice the data. We need to get the slice points like G code, M code in case of a CNC, or even in case of some of the desktop 3D printing systems, we need to get the G code, M code. And for that, your calculation will be simple. Your math involved, your computational efforts are simple if it is STL file. Several people will be asking, sir, why only triangles? Why STL file? Why only triangles? Why can't it be curve, right? So where you can, you never say miss any data. Your error is zero, right? But anyway, that ASTM is doing to a lot of exercise in that to replace the STL file, but still it is not happening. Like even though you have a AMF, you have a 3MF, those other file formats, but commercialization of that, it is not done so far. But anyway, your data should be in STL file. It should be getting converted, your CAD model representation into an STL file. And the third step is we need to transfer that data. So you have a software, interfacing software, along with the machine, which the vendor will be supplying, right? So then that in that interfacing software, just you export this STL file, and now you set the parameters. So what is the layer thickness, and if it is a laser system, what is the laser power, and what is the hatch space, what kind of a tool path. There is no tool here, but the name, this is a CNC. The DNA of AM comes from CNC, right? So then people may call that as a tool path, but it may be a laser path if it is a laser driven system. So then you set all that process parameters. So what is the layer thickness? What is the orientation? If at all it requires some supports, you set up all that. The fourth step will be the machine setup, or something like a G code, M code. That should be sent to the machine. But you are not writing a code right from the scratch in case of a CNC. But you are not writing that kind of a thing here. Just simply your software in a single button. So it is getting generated your contour data or cross-sectional data, and then that will be sent to the machine, right? So where in the fifth step is physical realization of that that data that you have simulated the data here, right? So that is then a digital simulation here, and exactly it is getting fabricated layer by layer, right? So that's what you do. So then building, it vary from one process to other process. The feedstock material is different. The energy source may be different, laser, electron beam, or thermal energy, or heating, or maybe ultrasound, ultrasound, like you may use some sonotrode to join. And nowadays you have a welding also, TIG welding, MIG welding machines can also be retrofitted like additive. But like say, whatever it is, like it should be physically realized in this fifth step, right? And the sixth step, we need to remove that part from the unloading, and then we need to do a post-processing. Post-processing in the sense like you have some unused powder, or you have some supports, or you have some resin, liquid resin is still, it is in a liquid stage, which you need to post cure it, like say, or sometimes you're not satisfied with the properties that are coming from as built component. So then you may use some heat treatment if it is a metal, and it may be a post curing, it is as a polymer, and depends, or it may be hipping, that depends, like or short pinning. So you use some post processing method, and your part is now ready, your component is ready. But in this case, it is simply serving a coffee. You may not much expect these properties, but it is a aero engine component, which it is going inside the aircraft engine or automobile engine, right? So where we need to have all this kind of a stuff to get these mechanical or the quality of the parts that you are getting on par with conventional, or at least after post processing, we are trying to get that. Okay, so these are the broad steps which we'll talking about. And coming to the AM processes, so processes, ASTM has classified into 7 groups. So you have a binder jetting, you have a direct energy deposition, and the terminology also, they have standardized this AM terminology, that is the ASTM 52900015. So they have standardized this into 7 groups in terms of terminology. They have grouped them in some logic. And the previous classifications by Marshall Burns or Chua Chike, but those classifications may be based on the energy source that you are using it, or the feedstock form. It is a liquid, you call as a liquid based systems, or it is a powder, you call as a powder based systems. And if it is a solid, like a filament or wire or maybe sheets, then you call as a solid based system. But ASTM has standardized this the processes into 7 groups. And talking about the materials, so you can start with polymers, both you can have a thermoset plastics can also be processed. Thermoplastics can also be processed, and metals can also be processed. Metal alloys can also be processed. Ceramics can also be processed, and composites can also be processed. So apart from this standard for engineering materials, so you can have an additional advantage. You can make a functional material like electronic circuitry or a shape memory alloys and so on. And not only that, you can make some natural materials, biological cells or tissues or organs nowadays. And it may be a food printing, right? Or it may be construction waste material made for building the constructing the buildings or the structures or the bridges. Normally people are doing a lot in this direction. So you have the material, as far as the material is concerned, you have a lot of flexibility. Even not only the standard engineering material, you can go with this kind of material, right? And the feedstock may be the powder form, or maybe a filament, that's a wire or a rod, or it may be sheet, or it may be a liquid form, right? And that should be done through some standards. The ASTM standards has been evolved. Just like that, you cannot made your filament by using the extruder, but you need to follow the ASTM standards, even for the powder also. What could be the distribution of the powder granulars, and what could be the shape and all that, which we need to follow the standards in order to prepare this feedstock. And for the sheets and the liquids also, what is the viscosity, or like say where we need to say follow that standard, right? Just like that, you cannot use as you can get it from any source, and then right, so which we need to. And if we talk about the within the single step, so through polymers, all the 7 groups like material extrusion, material jetting, powder bed, binder jetting, material jetting, vat photopolymerization, sheet lamination. So my talk is not about the processes, but it got a requirement. If you want to design for additive manufacturing, you must know about why, because each material will behave differently. And each process, so the surrounding envelope may be different. So altogether, you need to select your process, right process to your right product, right? So anyway, maybe other speakers may be talking about all these processes in detail, but I'm not going to talk in detail. But an idea here, so you can make polymers directly in a single step. What do you mean by single step? So without subjecting to any infiltration for improving the properties, or any other post-processing. As built, you're going to get these polymers in all the 7 processes. So maybe what kind of a material is a polymer, and then the state of fusion may be thermal bonding or a chemical reaction, or then the material feedstock maybe how do you get in the filament form, or melted material, or a powder form, or again maybe liquid, or a liquid material, or sheet lamination, and how you are distributing it, maybe through nozzle. You call that as extrusion based system, otherwise called as FDM, is well known under this process, right? And then print head, so means you have a multiple jet, something like an inkjet printer, right, where it will sprinkle or where it jet the material. Normally it's a liquid material which it will be jetting through this print heads, that in case of material jetting system. And it may be a powder has been spread in like a bed, and then you fuse it selectively. So then you'll call that the powder bed system. And use some binder. So you don't have a laser here. So if you see here, this is a sheet, you are sheeting rather than melting, and you are jetting it here, and you are melting the powder particles here, and you are binding the powder particles together. No laser, but you are using some binder in combination with the polymer or ceramic or metal. So use a combination binder to get the bonding between the powder particles maybe, or the layers, between the layers, so which we need to, that's what you do in a binder jetting. And you do a material jetting. And anyway, you have 2 methods to do this, maybe through this thermal bonding or through the chemical reaction bonding in case of a VAT-based system or SLA system. So where you have a liquid photosensitive polymer, it will get subjected to photopolymerization process, and you'll get your liquid is getting converted into a solid, right? So through a curing process, that's material jetting. And you have a VAT system, VAT photopolymerization process, where you can do it. Or even you can have a sheet lamination process. And of course, DED is not mentioned here. That is the 7th thing, which the material jetting may be repeating here. So you have even the DED, directed energy deposition. It is similar to welding, right? Probably the other speakers may be talking about wire arc additive manufacturing, and you have through a wire or a powder blown technology like that's. So instead of putting a bed of powder here, you will be pumping the powder and simultaneously you will be melting. That's called a DED system. But anyway, why it is not mentioned here is, so that is exclusively meant for metal systems, but we are talking about the polymers, right? So polymers, 7 out of 7, 6 processes are capable of doing, but only the one process, that is DED, that is predominantly meant for metals, but not for the polymers. But if we talk about the metals, like you have, this is what I'm talking about, this guy, DED, Directed Energy Deposition, where you can make in a single step your metal parts. And nowadays, material jetting can also capable of printing in metals in a single step. And of course, powder bed, it has been doing from several long years. And sheet lamination is a technique for single. And here varies, like, say, you may use some electron beam as a source or a laser as a source, or sometimes induction heating or electron beam, laser, ultrasound, like sonotrode. You may use solid state welding to join these sheet of material or tape, that the metal tapes which you can join, right? So this is a single step process, or you can multiple step. Maybe you can say add some, what you call, like as built, and then you can get only the green part, and say you can do some composite material parts jointed with the polymer adhesive, like probably if you remember SLS, that is selective laser sintering. So where it's a combination, it's something like a metal matrix composite, right? So you can have a green part, and further you make as a brown part, and then you further do post processing if needed, or use some furnace sintering, or without infiltration, or with infiltration, and secondary steps which you need to follow here. It's not direct as built in a single step, but you can very well get this from these technologies, and after following this additional step, 1 or 2 steps, very well you can get it, right? So okay, then we'll quickly see some applications. So my intention is not focused on the applications, but my idea is to give some capability. Why this is needed? So means your design for EAM, that is next talk. So where we must know about these applications, right? Better you can get some idea like what kind of so coming to the applications, you have a consumer products, the area, and the consumer electronics is the area, like cell phones or consumer products, any consumer products. So where you can see a lot of potentiality in terms of additive manufacturing in consumer products and consumer electronics. The reason is customization, complexity in the products, right? So you have, that is a driving force here. And of course, if we talk about the automobile, so as we already discussed, like you have some conformal cooling channels where you need to make the die, or you make the die design for in that fashion, or some cooling ducts, and you have plenty of applications which we can talk about. Automobile, and of course medical is another area where a lot of customization. Each patient is unique in his anatomy, right? So then we need to design accordingly, a lot of customization, or even it will go to up to personalization level in case of medical applications. That is the you can find a lot of revenue through these applications. Maybe in consumer products, this is millions of euros, even with the medical. So as we know that the industries like aerospace, like medical, like automobile. So these are the 3 industries like which it is judging any economy, any country's economy, right? So it will depends on these industrial segments, right? And then again, aerospace, like you have a lot of lightweighting of the structures. Anyway, we are going to discuss that. So then you have a tool making or mold making industry where you have a lot of scope here. One is conformal cooling channel, as we discussed, and other applications maybe it may be like military applications, so it may be architectural applications, oil and gas, space industry, and consumer markets, like a lot of customization in your jewelry or any other areas where we need to have a lot of customization needed, right? So where you can, and you talk about the aviation industry. So anyway, this also we are going to discuss further, design for additive manufacturing approach. Right now you can remember that you have from the GE, they are stating that in a LEAP engine, one of the series engines they produce for Airbus A321, and there are around 19 nozzles per an engine, and say they are quoting that through additively manufactured component, it is 5x durable and 25% reduction in the weight, right? So weight has been reduced and durability has been increased, and 20 parts now it has made a single part, right? So you know the advantage of reducing the part count in a product. And lightweighting. So lightweighting, not only production cost of the system, and it also a fuel consumption is also reduced, right? So the payload has been reduced. So like one nozzle, this much thing, and you have 19 nozzles in the system. That is just one component we are talking about, right? So anyway, and then we will discuss further how we are going to design for additive manufacturing. Why? Because conventional design is totally different. Like you used to have 20 parts, right? So the 20 parts now it has been consolidated into a single part, that is to a design for additive manufacturing approach, right? And we'll discuss some constraints, and that if time permits, we'll elaborately talk on that. Like say, even you can have even a combustion chamber part. Like it is not only the nozzle component, fuel nozzle component. Even it could be the kind of materials that you are using it now, super alloys, a nickel-based alloy, or aluminum, or a titanium alloy. So you can easily do it. And it is not only the engine components, even you can go with the structural components, right? This is one of the structural components where again took the advantage of bionic design, nature-inspired design. So this is one of the case study from Airbus, so where they are able to reduce 15% weight with the conventional design they had. Through additive manufacturing, they are able to 15% reduction in the weight. That is structural element, right? So even the same case for the cabin components, maybe a seat mold or maybe a belt, even buckle, right? So where we will talk about that also. So even as 1 gram of saving or 1 gram of weight reduction in the aircraft, maybe in terms of structural, in terms of cabin components, or in terms of engine components or underwood components, or so you can save a lot of fuel, right, for the lifetime of a aircraft to take it maybe 20 years or 25 years, and you try to justify the cost that you have incurred towards additive manufacturing, right? So anyway, then you have 1/3 of the engine parts from the GE Catalyst engine series. So they are now 1/3 of the engine parts are producing through additive or 3D printing. So they started this project in 2015, and they have completed. Recently, they got the certification from Federal Aviation Authority, FAA, and here you have a lot of simplified supply chain logistics in terms of conventional maybe machining, maybe casting. So where you have a lot of supply chain reduction, or the logistics got simpler and assembly got simpler. You made 20 parts as a single part, and your assemblies got simplified. And of course, you know, the reduction in the part count, your maintenance is also simplified, and your weight also reduced, right? So you have more than 100 lb of weight has been reduced, and fuel burning efficiency is improved. Most importantly, so you are and not only reducing the cost, you are increasing the performance of the system. That's what your DFAM idea is, to add the value to the existing product, right? So then only you come to additive manufacturing. Simply don't take a conventional design, which is meant for conventional manufacturing, and producing it for replacing the conventional to additive. So it's not going to do any help. And even 10% more power. So where you can see even reduction in the power, right? So where you can get all these advantages. And very recent thing from Boeing 77 series, so that is the 9X engines. So they made say 300 parts, more than 300 parts has been consolidated, and more fuel efficiency engines has been now in this class of Boeing 7 series by GE 9X engines. Like you can see why GE people are say investing a huge on this additive technologies, especially metal printing, of course polymer composites also. And you have again the 9X series, which is certified by FAA recently, and which includes a 3D printed titanium aluminide kind of turbine blade, which it is a fuel nozzle tips. And you have GE has shipped maybe in August itself, like it is these many number, right? Almost like 1 lakh fuel engines has been shipped, right? So where we can see the aviation industry where they are going, right? So not only GE, even if you talk about Rolls-Royce, if you talk about Pratt & Whitney, and Boeing, Airbus, or you can see a lot of focus, attention on these technologies. There is another aviation application where you can see MGTD 20 series engine. So where gas turbine engine for the Russian unmanned aerial vehicle. So where the cost has been reduced 50% through compared with the conventional method, and 20x times faster production. The lead times, because you don't have much supply chain or the logistics, right? So then you can quote several examples like this. And now we'll come to this a unique capabilities of additive manufacturing. So you have a lattice-based structure, right, where you can see this is not a solid design. The reason maybe the manufacturability. If you have a solid block, so it will take a lot of time to additively manufacture, but it is a contradicting kind of philosophy, right? Additive and subtractive. And you are not only reducing the weight by adopting the lattice-based structures. This is one of the thrust chamber inside the your rocket engine. So where this is a nickel-based alloy in Inconel 718. So it is very difficult to do a CNC machining, and minimum post-processing is with the additive technology it has been made, and it is a monolithic structure which has been done, and it has been combined, the fuel injector and the thrust chamber, made it as a single part. And because of this lattice-based design, so you have improved the cooling performance of the system, and it has even the weight reduction is also happened because it is a bio-inspired or a lattice-inspired structure. So the cooling performance has been improved, and the light weighting has even further reducing the weight of the system, right? And heat exchangers may be a 22% say reduction in the weight, and the volume is also reduced here versus the conventional things. And you have a complex heat exchangers has been done through aluminum based material, and copper is also now additively manufacturable. So you have more lightweighting and the cost reduction, and even you can go with the 0.5 mm wall thickness also for the spiral design. So where you can have a lot of advantages, and it could be a kind of a bio-inspired, a lung-inspired heat exchanger, and so on. So you have a lot of freedom in terms of design, right? So your designer in a conventional manufacturing, which we need to compromise these innovative ideas of the designer by your manufacturer saying that no, absolutely it is not possible to make it, right? So you have a lot of design freedom here. And you talk about the medical applications. So we need to mimic the bone structure. For example, you want to replace a chest implant, you want to fix a chest implant, or a spine implant, a spine wedge or a spine cage you want to. But the biggest advantage here, you are going to mimic the bone structure, the bone anatomy of the patient, which he has. The bone is basically a porous structure, but it is a sandwich kind of a structure. You have, say, cortile bone is much denser than a spongy bone inside, which it is more porous, right? So where you can, that's what the people like Dimmers or Steiker or Anatomics. So these are the implant manufacturers. So where you can provide a customized solution for the patient specific requirement, right? So, and even for planning the surgery. So you have a lot of FDA approvals in the recent times for the software as well as for the products. So they're giving a clearances. So this is one of the, what you call, you have the heart surgeon. So who is a child heart surgeon. So normally call as a, this is a month baby or a day's baby, which should be operated, right? So how complex that surgery is going to be. So then you can make use of these models for planning the surgery, rehearsal the surgery, and implantation also, of course. And you have some orthopedic casts. Like again, you take the advantage of nature-inspired design, like say where it may be an aerospace application, it may be a medical application. So the prime requirement is the lightweighting of the structure, right? So lightweighting in terms of orthopedic casts has been done, and quite interestingly, in the recent times, in the drug delivery, so the personalized medicines, like which you can see, majority of the time you may be taking underdosed or overdosed these pills, but you can customize or you can personalize these dosages. Even FDA in the recent times has been given several certifications, clearances for 3D printed pills, right? So where you can see a lot of developments in this direction also. And the automobile, where you have some small series variable turboprop engines, maybe some kind of, though it need not be, it may be started with the luxury cars, like it may be an BMW or it may be a Mini Cooper for customizing the dashboard, or for small series production for the turboprop engines for BMW series engines or Mini Cooper. Customization, and of course nowadays you can see the commercialization is also slowly it is happening now. We can see in a near future, you don't find the rubber tires. We can see a 3D printed say rims. Of course we can do a lot of customization. If it is a winter season, you can customize. If it is a rainy season, or if it is a summer season, so you can customize for your wheels also, right? Where you can have that capability with this technology. And you can have a lightweighted structure in case of a Formula One car, cars, or it may be an intake manifold, exhaust manifolds of an automobile, which we can use additive technologies here. And it may be even for the tooling applications. Say, for example, you have some investment costing, you can make a wax pattern, or you can make even directly the metal through a binder jetting system or through a metal powder bed system where you can, or otherwise you can make a wax pattern from this and you can cast it. And you can make an injection molding dies. Maybe you can make the inserts for the injection molding or die casting dies, which you can make directly from the additive manufacturing technology. Or even you can make these kind of a wax-based sprues, and then you can have the castings, right? So where you can make these sand molds, sand cores, and this is semi-finished one. And you have the impellers, big sized impellers, the core, sand core, and for the part, the finished, final finished impeller, or even it could be a ring for jewelry applications, maybe the investment costing purposes, you can make this wax-based patterns. And even gold is also one of the materials in the recent times. It has been added in the additive manufacturing material data. You can add even, you can print them in gold, or even you can, a lot of customization may happen here, right? So even you can earrings. This is about a mass customization where you can see these customizations in a good number. You can do it, right? So even it could be a titanium or a platinum can also be printed in the recent times. So the precious materials, a lot of customization has been happening as per the customer's requirement. And you can do a personalization of the shoe soles, like where, say, you have either an athletic who needs a custom fit and his weight and for his pressure points, which you can very well personalize your shoes, right? So that's what even Adidas or even Nike. So they are started using this technology for personalization, or even for the diabetic patient, which we need to have some soles, customized soles, right? Where you can very well do customize maybe through a TPU material, or you can do a lot and biodegradable materials, which is environment friendly, and lightweighted lattice structures you can, and that is as for the user's requirement, right? So you can do that. Or even people are trying, or even printing the customized dresses, or for the fashion designing application, right? Where people are inspiring these dresses, maybe nature inspired, maybe some elephant inspired, or a crocodile inspired, or whatever. So, or fish, or whatever, let's say, which you can design. Why? Because, and then you can print it also. You can have the materials like nylon, or you can print polyester as one of the materials which you can print it. And even education, like people like in the universities, even these desktop-based, polymer-based systems, FDM-based, you know that because of the rep movement, or the Scott Crump patent has been expired, and then this has become very, people started replicating this FDM technology from long back, maybe almost like 15 years. And even for the metal also, it is getting expired very soon. So we can see some desktop-based metal systems also in very near future. But anyway, you can have this printer at your classroom, and quickly they can model, or they can download from one of the repositories like Thingiverse or GrabCAD, where these models are already there. Somebody might have shared in that community. You can be the part of that community by subscribing, and then you can download. It's already, you can also upload your designed models in that community, and just you can download and you can print it, right? So you have a printer at your classroom, so then you can teach like how a windmill work, or how a gear mesh will work, or how a connecting rod or how a piston movement. So you can do a lot of say a teaching learning process. You can do a lot of stuff, right? So that is where you can use this technology. And even people are trying to print the chocolates or printing the sugar candies or shoesies. So this is where this technology is now very much popular. But though it is not up to the much commercialization or much industrialization, but slowly it is picking up. And 3D printing in construction. Very recently, actually, Dubai has put a target that by 2030, all the constructions, at least 25% of their buildings as 3D printed like this. They already started 3D printing these kind of constructions, houses, or but at least by 2030, they are targeting 25% of their buildings should be 3D or additively manufactured or 3D printed structures. And in the electronics also, like people are trying to print the PCB boards, or even you have some capacitors, or you have some kind of embedded stuff also you can do. You have specific applications, specific machines, which it could even able to do all that stuff. And very small size to very large means you can talk about technology like a 2-photon polymerization, which will comes under a VAT-based system. So you can make even a 10 micron sized structures. Or you have another side. So people are building, constructing a building, a real sized building, right? So through a contour crafting technology, basically it's extrusion based technology. So you have two extreme size of the structures that you can additively fabricate it through the say micro size to the real world size buildings. And even people are trying to integrate the robotics technology into the 3D printing. You have much degrees of freedom, right? So majority of the commercial machines may be a 3-axis controls in all additive or 3D printing technologies, but you have more degrees of freedom once you have a robotic arm has been integrated. And even people are trying to use a kind of unmanned aerial vehicles is also integrating, like where you have a lot of degrees of freedom in terms of cuddling, swimming, flying can also be done. Like company like GXN, they're Denmark company, so they are trying to develop this kind of systems. And now this is the first part of my presentation, and coming to the second part of my presentation. So how many design approaches so that your additive manufacturing is having, right? So broadly, before that approaches, so let us summarize. So what are the mantra or the principles of 3D printing, or rather than the advantages, whatever you call? So definitely manufacturing complexity is a free of cost that we have been talking about right from the beginning. Whether it is a simple cylindrical structure or a complex structure like this, a bio-inspired structure like this, but the cost remains same. So you're not putting any extra cost in terms of the complexity. But that is the case in conventional manufacturing technology, right? So, but it is totally, the complexity is a free of cost. And what else? The variety is free. What do you mean by that? So I can make, say 100 geometries or 200 geometries or 1000 geometries, all are different size, shape, geometry, dimensions, but I can do it in a single go. Why? Because I am not writing a code for individual components. So I never mind what is the form, but I mind only the layer, right? So then absolutely you don't have all the varieties free of cost here, right? So, and you have a no assembly is required. So means like you are consolidating the system, like you are making 100 parts or making 20 parts into a single part without requiring any assembly at all. And zero lead time, because you don't have the what you call the supply chain or the logistics for very nominal, and unlimited design space. So this is where your designer has assumed, or he has in his mind, like the structure of an aircraft should be not a solid design, but it should be inspired from the nature or the bird, like say, which it is more into a lattice-based structure. So that is his imagination. But like your fabrication technology be the hurdle, should not be hurdle for that, like where you have a lot of design freedom here, unlimited design freedom. And zero skill manufacturing means you are not at all writing any code, but all the magic lies in the design, right? So in your digital data or in your a CAD model, and it is more compact, portable manufacturing, and it is a less wastage byproduct, almost like literally zero wastage. You are adding as per the demand, not removing the material, right? And you have infinite shades of materials where you can combinedly print a circuitry material and non-circuitry material in a single structure, in a single go, or in a single setup, or you can vary the composition, right? So you can make a functionally graded parts, structures. Like that's the beauty of this, and you can precisely replicate the physical replication is possible through this technology. So why I am talking about all these capabilities or the unique capabilities of AM means, while we are talking about the design for additive manufacturing, so whether you are exploiting these unique capabilities of AM in your design or not, means whether you are adding the value to the existing component or existing system, whether you are doing it or not, right? So that I can explain that concept with the simple manifold and hydraulic manifold. So this is on seeing this design, so one can directly straightforward say that this is not meant for additive technology. This design is meant for CNC, targeted to the CNC machining. Why? Because you have a huge lump of masses here. Means your idea is don't waste the material in case of a conventional manufacturing method like a CNC technology or any machining technology, right? But you are forced to replicate this part. So you are borrowing the conventional design from the guy which he has given to you, but he doesn't know about the AM, but he has given this design to you. And if you simply reproduce it, or direct replacement means sometimes you have the spare parts. You are not allowed to change the design, right? Right. So why? Because it has it's a spare part, right? So, and it should fit to that place only, and you are not allowed to change the design. Why you want to change the design? We'll talk to that. Say if we are using the same traditional solid design, so it will take 4.6 kg of material. Say for example, if you want to simply take this design and reproduce it in additive rather than a CNC machine. That is the one approach. You are borrowing the same design from the conventional guy and you are reproducing it. But you have a second approach called adapt for AM. So why you are adopting the design, or slightly you are modifying the design. So that is adopting for AM. What is that adoption? So I don't want to have a bulk or a lump of masses here. Why? Because so it will take a lot of my scan time, or the laser has to travel a minimum to minimum, say 100 meters for each layer. I doesn't want to do. Why? Because my laser scan time, my laser scan distance is 100 meters per layer. So it is costing me like anything. So my machine hour rate is so much, but it is said altogether, it is And then we may be blaming that additive manufacturing is very costly. Why? Because the service bureau might have quoted you that is a 1 lakh for this component to be produced. Because of that reason, I doesn't want to do that. So I want to reduce the 1 lakh cost into say 50,000 or 40,000. So then what I need to do? So then I need to remove this bulk of material. So without changing the functionality, say you have the manifold, basically it's a hydraulic manifold. You have the inlet channels and outlet channels. So you are not changing those stuff, but simply you are making a solid into a shell-based thing where I can reduce my weight from 4.6 to 1 kg, and the weight reduction has happened 78%. And my time is also be reduced. My scan time means my machine hour rate is been reduced. So I can even quote a 50,000 rupees rather than a 1 lakh, for example, in the previous one. But still, I can work out for design for additive manufacturing means I can even not only modifying the form, even I can work out for the functionality. So altogether, I am changing the inlet and outlet position. Why? Because so maybe because of the constraints in stride drilling, they might have used this, but need not be that. So you can very well altogether you have redesigned your intake and outlet manifold channels. So where even further you have been reduced to 0.4 kg now it is, and means 91 reduction in the weight. And not only that, your fluid flow has been improved. The performance of the system is also improved because of this the change in the form as well as the functionality. And not only that, the fitment of the assembly is also being changed. And now it has occupied a lesser volume than the previous initial design. That's where I can change all 3 Fs, that is form, function, fitment. All these 3 things I have made. So in that process, I have saved a lot of money in terms of material, means in terms of cost, means the production cost. That I will further explain how it has been reduced. So you have the solid block manifold. So that is the traditional design which you have taken from borrowed from the traditional guy, the existing user, right? So then you have borrowed. So because here it's a replacement, you are not allowed to change the any design modifications. So with that constraint, you worked out. But because of this huge lump of masses, so the scan time means your laser has to, as I already said, for example, 100 meters, the laser has to travel per 1 layer. So I have say 2000 layers. Imagine that. So my scan time is 191 hours is my scan time. And my machine hour rate may be $65 per hour. So then 191 into 65. So it may be coming this value. And so far I didn't add the material cost, right? So the material cost may be $70 per kg. So the material, the weight of the component is 7.4. So 7.4 into 70 plus what 10% wastage, that is in terms of supports or anything that some partial melting of the powder which is sieved out, and then anyway you added some 10% of the wastage, and now it is coming say $570. And so that is the material cost only. You add this and the machine hour rate, and then it is coming 15K approximately. That is the stainless steel 316L grade stainless steel material, but it is a titanium. It will go like anything, right? So, but anyway, here also it is not a simple amount. So, but instead of a solid, so I made it as a shell. So as we know that, so instead of a 100 meter travel in the each layer, so just I made only a 0.4 meter travel. Why? Because I have removed all the lump of masses. I have adopted a shell based design. So without hampering the functionality of the system, right? Wherever it contributing some which feature is contributing to my functionality. I am not removing that. So anything non-functional regions or the lump of masses, I am removing it. So because of that, my 191 hours has been reduced to 36 hours. And it is mesh hour rate, if you calculate, it may be this much. And now huge saving in the material. So material cost is this much. And now if you add these two, and it is, say, roughly it is a 4K. 15K has been reduced to 4K. But still, if you are more well versed about the guidelines and the thumb rules or the whatever the design for AM guidelines are available, and then because your experience, like say you have modified further, you have redesigned maybe slightly or more than 36 hours to 19 hours. And we'll discuss like the supports has been differently and the wall thicknesses are 45 degree, or you made something, you're much cautious about the known capabilities of AM machine and which machine, the selection of the technology, and based on that, you have redesigned this, right? So then with that, you could able to now, this is only the 2K, around 2K US dollar. So 2K and almost like 4K, and it is 15K. So this is a steel, but you talk about titanium or a nickel-based supralloys, so it is much costly, right? So, but my intention will be like, you don't blame the technology simply by adapting the conventional design and doing a lot of lump of masses and taking a lot of time and say blaming the machine. It's very costly. But what you can do, so then you can go with the design for additive manufacturing. So we need to follow certain guidelines. We need to follow certain thumb rules to do this, right? So means we must have a thorough knowledge about all these problems, right? Then only you could able to. Why? Means each material will behave differently, right? Each process have a different physics altogether, right? So then, okay, then first we'll talk about, so like this we can talk as other things also, but I'm trying to make it as simpler as possible, like which you can further put a more focus on these areas. And then part consolidation. So in continuation with our discussion, like again, you talk about this GE fuel nozzle. So now there's 20 parts has been made a single part, right? And 25% reduction in the weight and 95% reduction in the inventory. So they are producing 30,000 plus parts and shipping every year. This is a bit previous data, maybe 10-year-old data, but now by this time it should have been much demand for them. And cost effectiveness is 30% cost efficiency, means they could able to reduce the cost if you compare head-to-head comparison with the traditional. But in this case, it is not a mass production, we do agree, but it is a limited production, maybe a few dozens or maybe 100, maybe 200, 300, or maybe in this case, it may be 40,000 per year. Okay, fine. So which we can, they are saying that it is cost effective compared with the traditional manufacturing methods and 5x durable, right? So you have the improved performance, right? Reduced weight. That is, incidentally, it is contributing to a fuel consumption, right? Anyway, and even you have another example like 16 parts. This is the traditional design. So which is one of the some duct in again some aerospace component. So duct assembly, it consists of some 16 plus has been glued together, but now it is made as a single part. So then it is easier to design, right? And then we need to check the supports and other. We'll discuss that further. Like say, we never talk about the supports in a conventional manufacturing, but we need to understand the support structures, or we need to understand the orientation, how it is getting fixed, right? And we need to understand the laser paths, if it is a laser driven system, like all that, which we need to direct effect on the design, which we need to focus much on. Then further you can reduce the cost. So you adopt a design for AM, you can make it very a cost-effective product and with the increased performance if you compare with the traditional practice. That is the idea. But anyway, what are the value-added things here? It is easier design, less supply chain, no tooling, less labor, no assembly error, less certification, lighter product, and it's a better. Right. So these are the value-added traditional versus your AM designed one. And similarly, one antenna example like 100 parts. Can you believe that these 100 parts, traditional design, now they made with only single part, and that they used to take 8 months to develop. Basically, it is a brazing and EDM will be done here, but it's a few weeks. So just it has been done through a powder bed metal system, and where you have reduced 95% weight reduction, right? And production cost is reduced to 20%, and you have non-recurring cost has been eliminated to 75%, like where you can see a huge savings. And even 300 parts. Can you believe that you have an assembly? So it is like 7 assemblies altogether. It is 300 parts. But what they have done, so they could able to say consolidate the parts, all 300 parts into a single part, right? And with the weight reduction and all that stuff, right? So just this is an example which you can see. And then you are very good in tool designing. Probably as such, India is very good in the tool design aspects, casting itself. So, but still, if you could integrate this technology with the tool making industry, right, you can get further benefits. Like say, as we know that the conventional tool design, so you can make only the straight cooling channels. We know that we need to extract the heat from the mold, but instead of a straight drill channel, so you can confine the flow of the coolant in such a way that it is confining the shape of the component that is there inside your mold, right? So you are confining to the shape where you can reduce a lot of cycle time. So if you see basically cycle time, say means where your cooling stage, 60 to 70% of the cycle time goes towards the cooling stage, and where now you are targeting, you are reducing this drastically because you are confining the cooling channels as for the shape of the component, right? So, and of course you have other components, but you have mostly the cooling time stage, and that too you are reducing the cycle time, and not only reducing the cycle time. So because of your conformal cooling channels, and if you see how this internal process has been developed in case of a straight traditional cooling channels, where you can see a lot of say what you call because of that internal stresses, the distribution, the heat distribution is not uniform, and where you have end up with some shrinkage or some distortion or some sort of problems in your final part. But whereas you have redesigned this conformal cooling channels through this additively fabricated channels, and which is integral part of your die, right, or mold. So where you can see it is a very nominal what you call the stress distribution. So you have a uniform stress distribution or the temperature where you have minimized your errors like distortion, shrinkage, all that you have minimized because of this, right? And even you can design this conformal cooling channels in a single go while designing your die or a mold itself, which you can very well design this conformal cooling channels, right? So where we can get this. And you have this another automobile case study. Anyway, I will give these links. You can further. But you have a conventional design, like you have straight cooling channels, but now it has been conformed as to the shape of that, and a few conformal designing channels, which it has been the complex surfaces has been adopted here, is because of additive manufacturing. So which you could this is the numerical simulation results, traditional versus conformal channels, and which you can see the results, the analysis results. So where they are saying that minimum to minimum 10 seconds in the total cycle time has been reduced because of this conformal cooling channel. 10 seconds itself, it's a great achievement. If you talk about this is in a fraction of seconds, it will go, right? Your injection molding system, like the injected parts, like this is where you can make use. And then still, if you are using some powder bed based system, like which we need to talk about your the staircasing effect. Probably the previous speaker might have talked about something on this, like where you can reduce and you can design this tool by adopting the guidelines or the thumb rules of additive targeting to, say, for example, this component is targeted to metal powder bed based system, right? And then where we need to understand how the supports can be given. Can it be a self-supported structure? That is a huge achievement. Like that we'll discuss. Like, but if time permits, we will discuss that also. Like where you can have even the supports. How do you? This is a major challenge for design for AM guy, where he works for how you can tackle the supports. That too, it's a metal printing system. And then how you can tackle these supports, or even what is the minimum hole size that you can realize the entire circular. Otherwise, you maybe end up with elliptical or some a teardrop kind of a thing. But like, so we need to understand, right? Otherwise, simply you are giving this design to the machine and you are blaming the machine without knowing the constraints or the capabilities of the machine, right? So where we need to understand first, and accordingly we need to redesign sometimes, right? Or otherwise, right from the scratch we need to do, or tweaking the design sometimes, depends, right? And then you have the topology optimization nowadays is area like where people are using this lightweighted structures and bionic designs also, right? So where you can see this journey maybe started with the parametric modeling, and generative designs are now picked up along with the topology optimization, lattice-based structures, or biomimicry or bionic designs, like where you can see even some of the softwares can support the designing. But designing is not the goal. I want to fabricate, like say you have consolidated some say some dozen parts into a single part here, right? And you have reduced 40% weight reduction, and it is stronger, 20% stronger than the this traditional design, having some 12 parts or 10 parts or whatever. And now with this generative design approach, you could able to make as a single part and reduce the weight, and then the mechanical strength is also improved. And finally, how do you get manufactured? How do you get fabricated? That is a question, right? Where design, anybody can do the design, right? But how do you get manufactured? So can it be directly manufactured on AM, or sometimes we need to tweak the design, maybe with minor tweakings, or if not, sometimes depends, like say, that's where you have a lot of demand for the design for AM, rather than simply people maybe in the impression that AM is all about a push button game. Yes, I do agree, it's a push button game, but at least you can realize, maybe with my talk, maybe the previous people talk, maybe the followed speakers talk. So then if you want to minimize the cost, optimize the cost, and at the same time improving the performance, quality, or whatever, so then which we need to adapt this. Otherwise, by default parameters, it will give something and garbage in, and you will get a garbage out, right? So then what is the use? So, but anyway, then you have a topology optimized structures where you have a lump of masses. We have discussed a lot on this, like how you can, even you adopt a lattice structure or cellular based structure or any bionic design, so which it is with a single setup, with a single run, with a single build, you are able to make it, right? Otherwise, conventionally, it may possible with the exponential increase in the cost of fabrication in conventional I'm talking about. But sometimes it may not be possible also because of these complexity issues or more joints or whatever it is, right? Yeah, and you do have some packages that it can support some topology optimization. But anyway, our aim is not topology optimization, but that's a design philosophy. But why I'm talking about this is you can directly fabricate these topology optimized or generative designs or a lattice based or a cellular based or any bionic design that you have. Your designer might have taken inspiration from the biology, cell biology, or what biology it is. Like say you can comfortably, without adding any extra cost, so you could comfortably able to produce it, right? And then another area where which we must focus on is the simulation part of the CAM. Like you have a very few, but you have a commercial software. I do agree. Even we have a 3D expert software from 3D systems for the metal based system. But still, if you are looking for, but we don't rely, or like say, still if you are looking for some kind of a PSD problem where you have even commercial exploitation also, like where this is the area where you can do a multi physics modeling, and then you can consider your say heat transfer kind of phenomenon. You can find very few literature in this area. So you can even develop a model, multi-scale, multi-physics based model, and which is considering the distortion, model distortion and residual stresses. Why? Because you have, even though you are removing the lump of masses, but still your temperature gradients are high, right? So if you are working with say titanium or any superalloy, you may be operating your laser, and you will be melting point temperature maybe around 1100 degrees C, 1200 degrees C. So where one layer, current layer is at that temperature. But what about the lower layer or the adjacent layer or the beneath that current layer? So you can anticipate a lot of residual stresses. You can anticipate a lot of gradients, thermal cycles is happening, right? And then you have a lot of distortion you can find out. Can it be compensated? And then structures, the support structures. So again, it will the game of orienting, or even sometimes we need to check for the, but I have some slides, if time permits, I will try to explain that. So you have the model structures, support structures should be minimized or optimized, not saying minimized, optimized. Why? Because sometimes the support structure will act as a heat carrying barrier. Not all the time cursing this support, it is not correct, right? So anyway, and you have sometimes the recorder damage may happen if you're not done simulation properly, and just like that. But if you are working with the titanium powder goes around say 20,000 rupees per kg is the powder, and the steel may be costing you around 3,000 rupees, 3 to 4,000 rupees per kg, and titanium it will go all the way to 20,000 rupees per kg. But we don't have a luxury to waste these build tryouts, right? So where we need to have a number of minimum number of build tryouts, of course, and post processing. So the post processing cost, sometimes it may go 50% of the total cost or 40% of the total cost. So then because of the supports, maybe one of the reasons, then can it be minimized? Or then post processing effort, maybe you may be adopting some heat treatment or hipping operation or support removal, all that. So can it be much better optimization of the resources? Can it be done? But you have the softwares which it will be given along with the machine. right? Which we have been using the 3D expert for this metal 3D printer. But like they may be giving the set of parameters, say for example, for one material, one composition, but not for all. Say for example, I have a 316L, but I have a 17.4 pH, but I have a stainless steel powder with some other grade, or I have a 16.64 tie 64, or I have a cobalt chrome alloy. But say if I have a aluminum 10 mg, 8 mg, but these guys may be giving that too, it may not be applicable for all the geometries. Like then immediately we'll check for the ASTM standards, right? But you have very few standards available in this area. Then what is the answer? Then is not the challenge here, right? But anyway, in my talk, like you can find out some challenges, or otherwise it's a PhD level problem or your research problem, or writing some proposal, right? And anyway, you do have certainly some commercial softwares which are available to even simulate this, but I'm not sure whether it has been guaranteed you that the result will be. But anyway, from ANSYS you have Additive Print and 3D Systems, you have 3D Expert, Verifact from Geonics, and you have other stuff maybe for DZMAT, for polymer, but majority of the simulation stuff maybe for the metal systems like SimuFact from Hexagon. Even NetFab can also be done some extent, but SimCenter from the Siemens, these are some of the commercially available simulation stuff. And design for polymers, but I don't have only 15 minutes, but I made a lot of slides. But anyway, yeah, I will try to complete. I will go a bit faster, but otherwise I will give you some resources. You can even go through it, like and not only the resources is important, like say the hands-on or your user experience matters a lot. In spite you followed some guidelines or some thumb rules or okay, but still. So the biggest challenge which we face in additive manufacturing is anisotropic nature of the fabricated components, that is not at all there in conventional manufacturing. Why? Because so you are adding the material, say this is your build direction. So you made one sample in this orientation and you have another sample you made in this orientation, but you cannot get the same properties. Like your clip is very weak once you fabricate in this orientation, but the clip may be good strength and the spring action of the hook may be good in this orientation than this. But you have another possibility to fabricate this orientation. So this may be the best spring strength, but it may be weaker hook. But like where you have to compromise, or we need to come out with you are 100% you are not able to eliminate this anisotropy, but you can minimize some extent, maybe operating with this one of the parameters as a build orientation, or you can try with other process parameters which it could able to reduce it. This is one challenge which we can talk about. Even it could be polymer, may not be much of it's say altogether polymer as a different ball game, with the metal printing a different ball game as far as anisotropy is concerned. And within the polymer extrusion based systems, if you vary the material, it will behave differently, right? So these are the challenges which, and say if we need to have certain guidelines. You have the wall thickness, what could be the minimum wall thickness, like your injection molding and other process. Here also we do understand to follow. So again, even though you're not able to fully remove the lump of masses, but still you can manipulate with kind of angulation, so which we can give some 10 degree with the flat area that drastically reduces your risk of distortion. So say, which we need to understand. So we need to, as maybe with your experience or making some trial components, something, or you have a benchmark components. Okay, fine. You have to do some exercise. Why? Because ultimately you may be blaming. So you might have put your wall thickness, which is not possible with the particular machine or particular material or particular technology. But you may be blaming the machine, like it's not coming. But we must know the constraints, or you must know these things, right? Then only. So supports, as we know that where you have some overhang portions, and you do have certainly some thumb rule, like with respect to horizontal or vertical axis. So some angle may be 10 degree, or like it's a 45 degree or more than 45 degree. So where you can see the amount of support structure that has been needed once you vary the projection angle. So it is varying, right? So then, which we need to understand. So all these capabilities, and this is a different ball game for your extrusion-based polymer systems, or it may be different ball game for your VAT-based polymer systems, or material jetting polymer-based systems. And again, the supports, again, you have one orientation, you fix this orientation like upside down, and you need to give a lot of support. The green color one is a support, right? And where the yellow color one is actual model material, right? And sometimes, like say your surface area is less than 5 mm square, you may not require support at all. But you have a feature that is more than, the surface area is more than 5 mm square. So we need to provide the supports, right? So, okay, fine. Then, which we need to understand. So if at all you change the orientation, or you redesign it as per the constraints of, if you are targeting to particular machine or particular model of the machine or particular material and so on, so material, like which we need to tweak the design, or otherwise what you are going to do. So sometimes it may build, and with the cost is increased fashion, or sometimes it may be design, the fabrication failure, or some damage of some features. And then you have a polymer, say for example, I have a 0.5 mm slot here. My thickness is 2 mm, thickness 2 mm. So whether it is 0.5 mm slot or 0.8 mm slot and 1 mm slot or 1.5 mm slot or 2 mm slot, it has been realized. But at the moment I increased 2 mm to 4 mm, my thickness of the plate. So this has not realized. This feature has gone, right? And further, if you increase my the sample or the build plate thickness is 6 mm. So the 2 features gone, right? And further, if I increase to 8 mm thick plate, the 3 has gone. And further 10 if you increase, and almost like it has started, this feature also not coming properly, right? So like we need to understand like what are the constraints of each and every process. Then accordingly we need to redesign. No other way. Or you have certainly some ribs and wall thicknesses, and you do have some rules, guidelines for the rib designing, right? And we need to follow, like it may be a kind of carving out the thickness of the ribs, or like say, which we need to follow those guidelines under the, and we need to provide some salt shaker kind of a holes. If it is through a powder bed system or through a VAT based system, so there will be an entrapped powder or a liquid will be there inside, then which we need to evacuate that after fabricating. And then you talk about the metal, but definitely you have to consider your laser beam diameter to compensate this, and what is the hatch space. So if you go, you have a lot of process parameters that is going to affect your, say, mechanical properties like density or strength, and your other properties, right? Where we need to understand, and accordingly, and again, it depends on type of material also. Steel will behave differently, and the aluminum will behave differently, and titanium will behave differently, right? So the absorption rates of the laser or the photon energy is different from one material to other material, and geometry to geometry, which we need to. And then you have this hatch space or hatch space or even the parameters like the toolpath strategies which we need to have to change or optimize. You have plenty of strategies which we need to work out. So the manufacturers may be giving a some set of process parameters to some material, or once you change the composition, that won't work out, right? So you are trying your own material or by changing some composition. So that is happening. But earlier days, like there will be a lot of monopoly. We have to buy the material from the vendor who supplies the machine. So those days are gone. But you are trying your own material. But then which we need to exercise a lot on these parameters anyway. And you have say CAD models from 45 degree, maybe 55 degree, 50 degree, 45 degree is fine, and 40, but where you are without a support structure, if you are trying to build, which you can see how this, what happened to this feature. It's already totally gone. If you are going with 25 degree, 20 degree, or even 30 degree also, where it started deteriorating, or it's not realizing this, right? And similarly, you have some overhangs, so which totally it has gone here, right? So where we need to understand. And you have some unsupported bridges. So maybe 1 mm is fine, 2 mm is fine, but if we start from 3 mm or 4 mm or 5 mm, it has started going off, right? And then you have the culprit here is a lot of residual stresses, which it has been built inside the component, maybe one layer, another layer, or because of that, your part has been splitted or from the substrate or from the, even within the part, which you can see there is a huge say detachment or a split of the part has been happened because of the residual stresses that has been built inside. So then how do you tackle these residual stresses? Just you can change the strategy, the laser filling strategy. So means like but I don't have much time to discuss, but definitely you have several things which you are, so if you are targeting to we need to compromise with the build time versus your, say, the stability, or which we need to optimize these parameters, right? And anyway, uniform thickness, there is another rule which we need to reduce, or the residual stresses, you redesign it. So why you want to redesign? These are the reasons, or these are the circumstances I'm trying to say point out here, like say where we need to do all that stuff. Or of course, this is always there, like you reduce the sharp corners, minimize the sharp corners, or you make it more into a kind of a filleting or rounding of. And even again, stress concentration and the cracks are huge here, uneven thicknesses, but again, you make it say uniform thickness across the structure. And then if your diameter of the holes are small, then fine, 2 mm, 4 mm, 6 mm is fine, but 8 mm, 10 mm, are you able to see your circular features are not coming here properly? So further, if you increase 20 mm, so totally it has been gone, right? So these, you may be anticipating a horizontal hole, but you may end up with some elliptical or some teardrop kind of shape, right? And okay, then in that case, we need to understand, we should not go, say, beyond 8 mm. That is for a particular material or a particular machine, like that. And elliptical, okay, fine. So 2 times this, and okay, we can realize. And teardrop, anyway, no problem, no issue at all. You can do it on diamond shapes, and you have certain guidelines, certain rules which we need to follow. And then part positioning guidelines. So normally, this is targeting to powder bed based metal system. So you don't keep your don't place your part which is perpendicular to your recoater direction. Just keep it some angle. This is the right position. And even don't inline these components. There are 4 components to build, but don't inline with this, and like this better You give some spacing and like this, but again, the recoating and other issues maybe, and other stuff which we need to, but this is the way which we need to rearrange it, or sometimes your recoater will damage your the part surface, which you can see these are the damaged because of your recoater blade or the roller has been damaged. So your part finally, right? So then where we need to follow certain guidelines, otherwise we may be held up with this kind of defect part, or maybe some cracks or some damaged surfaces on top of your components. And the tallest part must be very close to the recoater, but don't keep this tallest part away from the recoater. So I have a recoater here, like which is certain guidelines which we need to follow for placing or organizing your build area. And some common defects, like you have some balling phenomena, which you can notice it's not a uniform layer that you are anticipating, some some ball kind of appearance. It's not a full layer you can find. Reasons or several, maybe the residual stresses, or which we need to optimize these laser parameters, as well as maybe the material things, or some keyholes may be observed, or some oxidation. Always you do purging it, maybe by inert gas you evacuate or create a vacuum. You do several stuff, but still the challenge is oxidation, chemical degradation. You can find some cracks, delamination. Just now I showed you in the previous thing where you have derailed totally from the substrate to part, or within the part it has been split, right? And some distortions which you can find because of huge residual stresses inside, and some inclusions may form, and poor surface finish, porosity. But porosity, you can have a controlled porosity. We can achieve that. You can talk about a positive aspect, but anyway, so you have some common defects that you can find in 3D printing process, right? But let's say you can find some people like Purdue University, they have come out with design for AM guidelines. They have divided this into several areas, like where, 1 minute. So you have a complexity as one of the criterions that they have. So complexity and other, sorry. So they have a matrices here, like where just if you send your part to them, so it will be evaluated with the various criteria like complexity and other criterions which it has been, and then the thin features, stress concentration, tolerances, geometric exactness. So then it will give you the score. So if the score is very low, then no problem. Without redesigning, you can fabricate through additive technology. But like if the score is high, sometimes which we need to minimum modifications are needed. But if the score is too high, we need totally redesigning of the part. So fabrication challenges. So you have several challenges which we, right from the material given challenges. Maybe you talk about powder particle size, maintaining it, and purity and distribution and other stuff, and the design related stuff. This is where your design for AM is going to play a major role. Like how do you minimize your overhang, support structure, and improving your say reducing the build time, means reducing the cost of the production, right? And you have the layout. Just now we have discussed like how do you organize your components and the process related parameters. So you have around 180 plus parameters that it should be optimized. But that definitely it's a challenging stuff. And then post to processing, heat treatment, short pinning, polishing, and other stuff. Like so you have some considerations, the tension, curling, heat dissipation, stair stepping effect, anisotropy, as we already discussed, and volume contractions, micro melting. So you have several considerations that we should. And then you may get doubt, sir, is there any ASTM standards or ISO standards? Yes, you do have ASTM ISO standards, though this technology started early 80s, but you can hardly find around 45, 50 standards. The ASTM and ISO very recently, in the sense, though this technology is 35-year-old technology, but ASTM, ISO, they started developing these standards maybe around 10, 15 years ago. They started. So still, you can find some, but it is not sufficient. So you have a design-related standards and terminology-related standards, design-related standards. Like this design-related standards or feedstock-related standards or fabrication-related standards. So you do have certain standards, but still it is not going. Why it is not going much industrialization? Because of these challenges. The standards are very few. And you can find, say, this is a fishbone diagram, like where you can see, like right from the operator to the building process, or even the designing, or even the part level, or AM system level, or material level challenges, like which you can find several parameters that ultimately it is getting your part quality, right? So, which we need to best or optimize these parameters, then you will get a very good quality with reduced cost. So that is the conclusion where we can put it. But still, I might have given some sort of challenges, or I might have thrown, at least during this 2 hours of my talk, I hope I have given some idea on this area, especially maybe you can find these challenges could be taken it as a research problem you can work out, right? So then maybe let me summarize what I have done for the past 2 hours. Like we started with talking about the importance of the 3D printing in Industry 4 and steps in 3D printing process and the various processes and applications of 3D printing, and realizing the capabilities of AM, maybe part consolidation, maybe a sort of conformal cooling channels in particular applications like aerospace, automobile, medical, or so on and so forth. And design approaches, like it could be like a kind of direct replacement or a spare part production, or maybe adapt for AM, or the last approach is DFAM, that is design for additive manufacturing approach. That is going to be the highest advantage which you are going to get if you adapt that design approach, right? And of course, which we have discussed, some topology optimized structures and bionic designs. So in order to achieve this, and we need to follow some guidelines, rules, maybe different from polymer printers to metal printers, and some fabrication challenges. At least I hope we have discussed some part, but not all together. But like, yeah, of course, which you may hear a lot from the other speakers, right? So during this 2 weeks of this program. So yeah, before concluding, so we have a metal 3D printing facility that is from 3D Systems DMP Flux machine, the powder bed based metal 3D printer. And we do have a couple of Stratasys make machines, that is the Dimension series, and another one is a Mojo series. And we have other desktop based 3D printers like Ultimaker 2+, and we have other FlashForge, and we have other couple of desktop based printers for polymer printing. And scanners, AnyScan, SenseScan, 3D scanners we have, and muffle furnace for this metal printing post-processing. We are using it, and short pinning machine again for the post-processing in order to improve the quality of the parts. And we have a dedicated software. So we have a Mimic software for medical image processing. we do a lot on the medical, but unfortunately, I was not discussed that part here. But we developed along with the collaborators, the hospital people and the dental and medical colleges. We developed patient-specific implants, devices, and we filed the patents. And recently also we have one US patent has been granted in this direction. So, but anyway, that is not the scope of my presentation at this point of time. So we do have a Mimic software for medical image processing, and we do have a Magic software, and we do have a Thematic software, all basically medical image processing and medical device manufacturing. And even it will be worked out for a lattice-based designing. That's what where the medical, you have a lot of potential to work on those. And we have Catalyst software, and simulation software is really expert simulation software. Yeah, that's all from my side. And we have a YouTube channel also. If you are interested, even you can subscribe to our YouTube channel. I will post this YouTube channel link in the chat box. If you are interested, even you can yeah, subscribe to our YouTube channel. Yeah, that's all from my side, sir. It's over to you. Yeah, definitely you may be interested in asking several questions. I know that. So yeah, it's over to you, sir.
Sir, thank you for a very informative session. We had a great session with the knowledge of the importance of 3D printing in the 4.2 industry, the steps what we involved, especially about the DFAM. You said the importance of DFAM being a very crucial part in learning about this additive manufacturing, sir. Now, I request the participants, if you have any doubts or queries, you can just switch on your mics and post your questions. Participants, if you have any doubts, you can clarify your doubts. Or you can even post it in the chat box so that we can convey the questions to sir. I think there is no questions from the participants. Sir, I will share your email ID to the faculties so that if they have any questions in personal, they can put a mail to you and then come in contact with you, sir. Sir, thank you once again. Thank you. A very informative session, and we look forward for further assistance, sir. Thanks a lot, sir. Thank you.
Thank you.
We are formally concluding the session, and the next section continues tomorrow. Thank you.
Thank you, sir.
Yeah, thank you. Thank you very much. Thank you for the opportunity. Thank you. Bye-bye. Have a nice time.